All right. Going off the chapter 13 stuff we started on Monday. We had 4 principles of experimental design. You were supposed to have a control. You're supposed to randomize. You're supposed to replicate your experiment in 2 ways. And then if you needed to, you could block. All right, which we can group them. When you're designing an experiment, you're going to have to write out your explanation, but sometimes it's nice to draw a diagram before you explain it. So you can have an idea of what it should look like. Then you can go back and explain all the little pieces. All right? So if you have an experiment that you're going to design with a diagram, and on one of the activities I gave you, the backhoes and forklifts, it says to create a diagram after you've done the explanation. All right? So this is what it's talking about. You're always going to start off by having random assignment of some number of subjects of experimental units or something. So I will show you an example in a little bit. Okay? Then you're going to randomly assign those subjects and however many groups you have. Your groups are going to correspond with a treatment. So if you have 4 treatments, you're going to have 4 groups. Okay? So you'll randomly assign those subjects to groups. Once you've assigned subjects to groups, you're going to randomly assign them to treatments. You aren't just going to say, this group over here is going to get a placebo, and this group over here is going to get this treatment. That introduces bias for like personal decisions. So you always randomly assign your groups to treatments. Then after the experiment is conducted, you can go back and you can compare your results from the treatments. Okay? So this will make probably a little more sense when we put one into practice. But sometimes a diagram can kind of have everything laid out for you so you can answer certain questions. Okay? Questions about what a diagram kind of looks like. We're going to see some today. All right. Now, I'm going to do an abbreviated version of this example. The example is all written out nice and neatly in your book on page 297 is where this starts. I normally would not do the examples in the textbook because you should be reading the textbook and should be looking at them anyway. But this chapter can't help itself but to talk about this one example over and over and over again. So we're going to do it together. All right? So we're going to actually go through and do experimental design to make sure you have all the key pieces. So an ad for Optigrow plant fertilizer claims that with this product you will grow juicier, tastier tomatoes. You'd like to test this claim and wonder whether you might be able to get by with half the specified dose. How can you set up an experiment to check out the claim? Of course, you'll have to get some tomatoes, try growing some plants with the product, and some. But you'll need a clearer plan than that. How should you design your experiment? We're going to design the simplest kind of experiment, a completely randomized experiment in one factor. All right? So that is the same thing as having a simple random sample. The most basic experiment is one that's randomized and only has one factor that you have to worry about. Okay? So I'm going to give you some information that they provide later in the book, and then we're going to draw a diagram first, and then we'll go back and identify some things. Okay? So this is what you're going to know. They have 24 tomato plants for you to use. All right? So from those 24, we're going to design this experiment around these 24 tomato plants. All right? So I'm going to draw a diagram first. And then we'll go back and explain. So we're starting with 24 plants, right? How many treatments are we going to have? So let's think about the treatments. How many treatments are we going to have if we're worried about this whole fertilizer situation? What does one of the treatments have to be? No fertilizer. You have to have a control, right? So you have one treatment is control. That's good to make note of. What's another one of the treatments going to be? What was he asking about? He wants to see if he could get by with half the specified dose, right? So one of them is going to be a half dose of fertilizer. But then there's going to be another treatment. What's the other one going to be? A full dose. Okay? So since we have 24 tomato plants at our disposal, if we're going to draw a diagram, what are we going to do with those 24 plants? We're going to randomly assign them to 3 treatment groups, right? Do they have to be even? No. We have 24, and it's divisible by 3, so why not? Okay? So how many plants are going to be in each group? 8. So this is going to be random assignment. And we're going to have group 1, group 2, and group 3, and they're going to be 8 plants apiece. Everyone with me so far? Groups, we have 3 groups of 8 plants. Those groups have to be assigned to treatment, right? So you have random assignment again. And this time they're going to be in treatments. So you can number them, name them, make sure everyone knows what they are. Then the whole point of this experiment is to compare what? If we go back to the original question for a second, what are they trying to figure out? What's the claim? Juicier, tastier tomatoes. So we're comparing the juiciness, did I spell juiciness? I don't know. And tastiness of tomatoes. Okay, so that's what we're going to talk about. So now I have a diagram, so we at least kind of have a little bit of an idea of what's going on, right? We have the basic layout of what's happening. Again, this is not going to suffice on the AP exam because there's too much stuff you still need to explain. All right? So the following things need to be written out. I do not have the time today to write it all out nice and neat, so I'm not putting the complete sentences, but you would. All right. We need to start with the 24 plants. What needs to happen with these 24 tomato plants? They need to be the same type, right? Should be the same type, come from the same environment, right? Should be approximately the same height or same growth, right? You want to start out with 24 tomato plants that are as the same as possible, right? Why is that important? You're trying to reduce variability to begin with, right? You're gonna have a little bit. There are 24 plants. Every plant's different, but you're trying to put them all together. Come from the same environment. All right. Then it says in our diagram we're going to have random assignment to groups. How are you going to accomplish that, though? You say you're going to do random assignment, but how are you going to do it? Okay? Assign plants, number 0, 1 through 20. Use a random number generator. 24. Sorry. To select 8 unique plants for each group. Why is the word unique underlined? Can't have the same plant twice because you can only use it once. use. All right, so once you have random assignment to groups, it says you're going to have random assignment to treatments, right? Yes. So then you're going to randomly assign groups 1, 2, and 3 to a treatment. Right? You might want to put the treatments are control, which is no fertilizer. I guess I don't need the parentheses yet. You have a half dose group, and you have a full dose group. So just for vocabulary purposes real fast, what is the factor in this experiment? We said this is a one-factor experiment, which it is. The factor is what you're changing in the experiment. So this is the amount of fertilizer. And so how many levels do you have? Okay. Again, that was just for sake of vocabulary. Okay. So going back to my diagram, I have them in 3 treatments. All right, so now I actually have to conduct the experiment, right? So if you're going to conduct the experiment, again, we're trying to control some things. You want, I'm just going to make some bullet points. You want similar growing conditions, right? Again, I'm trying to control variability, if at all possible. So if they're all going to be in full sun, they all need to be in full sun. Like one can't be in the shade. And you have the same type of like soil. So hopefully the same like plot somewhere. We're talking about tomatoes. I'm talking about juiciness and tastiness. So you're going to have to grow until they're ripe, right? You can't just stop a week into it because you feel like it. Then at the end, it said we have to compare, and we're comparing juiciness and tastiness. How do you compare juiciness and tastiness? What are you going to have to do? You're going to have to, are you going to eat them though? Okay, but are you going to eat them personally? No, why are you not going to eat them? Because that you're the one conducting the experiment, so you don't want to be the one that's judging the experiment, right? So you need to have like a group of friends or something, I don't know. Peers. The book says panel of judges to test your tomatoes, but you want juiciness and tastiness are a subjective measure, right? So what are you going to have to create to control the subjectiveness? A scale, like a juiciness. How do you spell juiciness? Juiciness and tastiness scale for your friends to use, right? That way you get numerical data, and that way you can like graph it however you want to, look at a diagram of your data, whatever, okay? So conduct the experiment, compare, you need to explain. So these are things you'd have to explain. So in the backhoes and forklifts prompt that you have 2 days to do, it says to make a diagram in there, but the rest of it, you need to, all the stuff you need to write out thoroughly describing what's happening in your experiment. Does that make sense? Yes? Okay. Are we good with the tomato experiment? Yeah? Okay. The rest of this is going to be most stuff we've already talked about, just in more detail. Okay? Yeah? Okay. I'll try to wrap it up as succinct as possible. From your homework last night, statistically significant. I don't want you to worry about that too much right now, and I won't put it on your quiz or your test, because after Christmas, when we're doing all of these tests, all this inference stuff I keep talking about, they're all tests for significance. So we're going to have a number that says, yes, this is a significant result, and no, it is not. Okay? So after Christmas, that's all going to come full circle back to here. All right? But for right now, you just say, okay, does the difference you observed in your experiment is that different, more or less, depending on what the scenario is, than what you would expect just from your day-to-day routine of whatever you're looking at? Okay, so is it way different is the general statistically significant definition. Okay? Again, we'll have tests for that later. So don't spend too much time worrying about this. I'll come back to this if we have time. Keep in mind some things about experiments and samples. They're not the same thing. So what you say can't be the same thing. Surveys are measuring some sort of population parameter. They're trying to take the results and extend it to a larger population. Remember, a parameter goes with a statistic that can be measured. So you want to know the mean of the population, so you find the mean of your survey and extend that out to your population. An experiment is just trying to assess the effect of a treatment, so it's not really for an entire population. This green box in your book that most of you guys wouldn't have read is really important. In a survey, we always pick random samples from the population, right? And that's appropriate, that's what we do. In an experiment, we do not select random samples from the population. Think about, you guys have enough common sense, if we were thinking about doing a medical experiment, okay? Do you just take a random sample of people from the population? No. You put out an ad or something and you ask for people that meet a certain criteria to volunteer to be part of the experiment. All right? So you have to be careful with that. So that's why you have to keep surveys and experiments separate. In a survey, you're asking for opinions, so things can get more biasy, weird. In an experiment, you're controlling a lot of things. You just have to have a certain type of person to start with as a subject. So it's not a random sample from the population. That's not how that works. Okay? We talked about control. You have to have a control group if at all possible. There are only a few examples of times that you will not have a control group. Your control is your baseline. If you don't have the control, then you don't know how your other treatments compare to nothing happening. Okay? So control is important. Blinding. We haven't talked about blinding, so we're talking about blinding for a second. This is the first sentence in this section I thought was very clever and true. Humans are notoriously susceptible to errors in judgment. So, because of that, we try to blind experiments. By blinding, I mean you withhold information from these people so different people don't know what's going on. For example, you guys are all in a medical study. You are all my subjects. I'm doing the experiment. All right? And there are 4 different possible treatments. And they're all pills, so they all look the same. I don't tell you guys what treatment you're getting. I just give you one. I know. You don't know. All right? So since you don't know, you can't make up some fake symptom or something because you have no idea what you're getting. All right? So if one group is left out, then it's a single blind study. All right? Now that could go with just you guys not knowing. It could be single blind if you guys don't know, and then I'm running the experiment, but I have someone it's a technician giving you guys the pills, and he doesn't know either. I've just assigned each of you, it says your name and then pill A, pill B, pill C, pill D. And so the person giving them to you doesn't know either. All right, that's single blind. That's fine. It's double blind when you have a different level of people that don't know. So in a double blind study, subjects don't know, probably, but also the people evaluating the results don't know. Okay? So I, the experimenter, gives Miss Speed, let's say, the results of my experiment. And all it says doesn't have your names, doesn't have anything. It just says, maybe I'm doing a blood pressure test, new pill, something like that. It has your blood pressure at the beginning of the experiment, and it has blood pressure readings throughout the experiment. It has your final blood pressure reading. All right? But nowhere on there does it say that each of you got pill A or pill B or pill C or pill D. She's just looking at blood pressure readings and comparing blood pressure readings. She has no idea what treatments were involved. All right? You guys didn't know what you were taking. She doesn't know what was involved. So it's double blind. So the only person that really knows what's going on is me. All right? So then I can go back and extend that later. When Ms. Speed gives me her analytics back, I can be okay, well, this group of people got pill A, and she said they improved the most, and so I have a better idea of what's going on. Okay? So, here are your two groups of people. People that could influence the results, the subjects, treatment administrators, or technicians. Because let's say someone knows that, like, if the person giving the pills knows that one works better than the other, then it's human nature. They might be like, oh, I'm just going to sneak other people to this pill too. All right? You don't want that to happen in your experiment. You want it to be as controlled as possible. And then you have those who evaluate the results. Judges, treating physicians, person that are going to run analytics on your experiment, whatever. So single blind, if one of the people in one of these groups doesn't have a clue. Double blind, if a person in both of these groups doesn't have a clue. All right? Questions about that? You guys all know about placebos? Yes. Placebo is a fake treatment that looks just like the real treatment. A lot of the time you see a placebo in some sort of like pill experiment because you can make a pill look like another one really easily. It's harder to give a placebo in like an exercise regimen, right? You can't have a fake exercise regimen. That doesn't work. So placebos aren't always in an experiment because you can't make something look like something else. Why we have placebos, though, is because of the placebo effect, and that's a psychological thing. So if you're taking a pill and you think it's the real treatment and you're feeling better because you're taking this pill, are you really feeling better? Is it psychological? You want to be able to compare that. So placebo becomes your control, so you can compare the psychological effects to everyone else as well. So the best experiments are a combination of randomized, comparative, double-blind, and placebo-controlled. Are all experiments going to be like that? No. Not even close. But if you can make an experiment have all four of those characteristics, that is awesome. Okay? Questions about controls, blinding, placebos? I think it'll help when we do some more examples. Okay. The next thing is blocking. We talked a little bit about blocking. So blocking is just like stratifying. We just call it a different name when we do experiments. So you can block by gender. So you have a group of males and a group of females. You can block by plant type. You can block by dog breed. All right? So different things, different groups. You call it a randomized block design if you're giving it a technical term, because that's what you're doing. It's a randomized experiment with blocks. So here's a diagram of the tomato experiment, blocked by the store the plant came from. So they could only find 18 tomato plants. They found 12, let's say, at Lowe's and 6 at Home Depot. Okay? But these plants are being kept in completely different conditions. Like Lowe's is watering them, Home Depot hasn't sitting on the clearance aisle. I don't know. But they're completely different. You didn't get them in the same place. They're not in the same conditions. So they blocked by location. So you have the same exact experiment going on in both sections. That was the experiment we designed earlier. And you have the same exact experiment going on at the same time with the other group. So you design it the same exact way. You have the same amount of groups, same amount of treatments, you're just doing it twice. Questions? So blocking, you have parallel experiments going on. That's the best way to think about it. And if you start adding more factors, we'll do some more later. The biggest we'll probably do in here is a 2-factor experiment. The more factors you add, the more combinations you have, so the more treatments you have. So here is, we added a factor of the tomato plants with watering. So no added water and then daily watering. And then you have the fertilizer. So now you have 6 treatments instead of 3. And if you're doing a block design, you have 6 treatments in both blocks. All right, so it becomes a little more complicated. The more factors you have, the more complicated the experiment is. All right. I'm going to do like 2 examples, and I'm going to give you the assignment. So number 7 through 20 says, read each brief report of statistical research and identify, A, if it was an observational study or an experiment, and it tells you what to do if it's an observational study, and it tells you what to do if it's an experiment. Okay? You wouldn't have to answer all these incomplete sentences because it's labeling it all out in separate sections for you. So number 7. Over a 4-month period, among 30 people with bipolar disorder, patients who were given a high dose of omega-3 fats from fish oil improved more than those given a placebo. Okay? So first of all, is this an observational study or an experiment? Definitely an experiment. So I'm just going to use what they have up here. Okay. Since it's an experiment, we're going to answer this set of questions B through H. So, what were the subjects studied in the question? Who are your subjects? 30 people with bipolar disorder. So on C, what is the factor and the number of levels? So what is the thing you're changing? Yeah, what are you changing in this? The omega-3 dose, right, versus a placebo, right? And so there are 2 levels, and those are the 2 levels, right? The factor you could just say is the pill being given if you want. So since there is 1 factor and 2 levels, then how many treatments are there? 2 treatments. It doesn't really tell you, but what would the response variable be? Yeah, it says improve, but improved. What? So it says bipolar, so maybe they were improving in symptoms of something. That one's kind of sketchy. They don't really tell you what they're looking at to improve, right? Does it tell you if the design is completely randomized, blocked, or we haven't even talked about matched yet? So is it completely randomized or blocked? Does it tell you? They didn't tell you how they put them into groups or anything, so I don't know. They don't tell us. Does it tell you if it was blind or double blind, or could you figure that out? If they have a placebo, then that means it's going to be single blind for sure, right? It doesn't tell us if the judges of the experiment or like the doctors knew. So it's definitely single blind. We know that much. If there's a placebo, then it's single blind because we're not telling those people what they got. And then the nature and scope of the conclusion the experiment can reach. Well, really, we don't have enough information about the improvement, right, of symptoms, but I could probably extend it to bipolar patients. I don't know, it's kind of sketchy, right? It doesn't really give us a whole lot of information to go off of. Questions about that? All right, now I have 3 more examples, but they all go with this one. So it's just referring back to this bipolar question. Exercise 7 describes an experiment that showed that high doses of omega-3 fats might be a benefit to people with bipolar disorder. The experiment involved a control group of subjects who received a placebo. Why didn't the experimenters just give everyone the omega-3 fats to see if they improved? What would be wrong with just giving everyone the omega-3 fats? Right. So in the short form, you have no baseline, right? You have no idea what would happen if you didn't. You have something to compare it to. All right, on 23, same experiment, a dietary approach to treating bipolar disorder. Researchers randomly assigned 30 subjects to 2 treatment groups, one group taking a high dose of omega-3 fats and the other a placebo. Why was it important to randomize and assign the subjects to 2 groups? What's the importance of randomization? Right, we're trying to eliminate bias, if at all possible. It's going to equalize the groups, right? What would be the advantages and disadvantages of using 30 subjects or 100 subjects, or 100 subjects instead of 30? Right, so we're going to have more data. That'll probably reduce variability, right? You have more people. But what would be a disadvantage? Time, money, human error, right? And then lastly, same thing. Suppose some of the 30 subjects were very active people who walked a lot or got vigorous exercise several times a week, while others tended to be more sedentary, working office jobs and watching a lot of TV. Why might researchers choose to block the subjects by activity level before randomly assigning them to the omega-3 and placebo groups? So what would blocking accomplish? Right, so it allows researchers to compare groups because maybe they work better, maybe the omega-3 works better in active people, right? And it allows you to control, if you will, the potential variability in groups.